Hello everybody, welcome back to another video for Computational Science 1. Today we're going over bisection. I'm gonna go over what it's used for, pros, cons, requirements in order to use it, the pseudocode for it, and also how to do it by hand. Of course, we always start with theory before we do any math or any code. So the first thing I want to start is what is bisection and what is it used for? So the bisection method is used to find the root of some non-linear function, though it can be used for linear functions as well. So for example, the whole point of bisection is to find the root, right? So if we have a linear function like this is the graph, like an approximation. This is, I believe this is 2. But let's see how you could do this algebraically. That was a struggle. But basically what you'll do is, here, let me write this down. F of x equals 2x. Okay, that's too thick. 2x minus 4. So if I tell you, can you find me the root for this? Where's the root for this linear equation? The first thing is you do, you'll set this to 0, and then you'll just isolate for x. And so this will be 4 equals 2x, and then 2 equals x. And so now you know that there's a root, right, at x equals 2. And as we could see, same thing here. And so for this one, you don't really need to use something like bisection. You could just do it quickly by hand, and you'll get your answer. For something like a low degree polynomial, you can factor, of course. So this is your original function. And then once you factor it, you'll get something like this. And then from this, we will know, if you remember your high school stuff, you'll have a root. So whatever this is, it's the opposite sign. So this would be x equals 2 and x equals 3. So we have 2 roots, right? And as you can see, I graphed it on Desmos. We do have 1 here and 1 here, 2 and 3. And so for low degree polynomials and even higher degrees, so this is 2, you could do for 3, you could also factor it. And obviously the higher degree polynomial you go, the harder factoring becomes. And then obviously the harder factoring becomes, that's when bisection becomes more of an option, like, hey, should I factor or should I use a different method like bisection or Newton's method, which we will learn later on. But there are some functions, transcendental functions or equations. These ones you literally just can't factor. Like, it's not possible to factor. So even if you wanted to, you can't. So if we look at this, right, and I tell you and the reason you can't factor is because cos, what are you going to do to factor cos? You can't really do much. And usually if I give you a function of just cos x, right, it just goes like this, it isolates, and it has multiple roots. And so it's like, okay, well, how about you find me the root somewhere? What do you do? You said this is 0, okay, then what? So you can't really do much. What do you, if you think you could do a cos inverse, that doesn't really work. So for these type of functions, that's when we use methods to find roots. And so this is the function for cos x. It does have a single root. Now, sometimes obviously cos x, like I said, sometimes it oscillates, multiple roots. But for cos x minus x, there's only one root at this number. So if you want to obviously double check that this is a root, you could take this, sub in here. Cos of this number will just give you this number. So f, so here if I go and I do f at 0.73909, obviously, and I sub them in. So this number will get subbed in here and subbed in here. Cos of this number will just return this number. And then obviously x is this number. So you're doing this number minus itself, which gives you a 0. Therefore, it's a root. So just in case you don't trust me or you don't trust Desmos, you could always just do that to confirm that this is a root. Okay. Now, how does this so-called bisection work, right? So obviously, we're going to use the same graph for that cos cos x minus x. And if you didn't know that this was a thing, right? So let's say this wasn't here. I'll just scratch over it. And I'm like, okay, I give you the I don't even give you the graph. I just give you the function, and I'm like, can you find me the root? Oh, what just happened? There you go. So what you'll do, the way bisection works, is the first step is you gotta find an interval. And the interval has to be, so your interval is gonna be a comma b, right? One of these have to be negative. It doesn't matter which, because your function can go like this. So this is negative, this is positive, or it can be the other way. Like in this case, this is positive, and this is negative. By positive and negative, I'm talking about specifically the y. So obviously the y up here is positive, and then the y here is negative. So you want to choose an interval so that one variable is negative, one variable is positive. Why do we do that? The reason we do that is because when you know, if I choose 2 points, if I choose a point here, and this is obviously positive, here, let me make this thinner. If I choose a point here, and this is positive, and I choose a point here, and this is negative, I know for a fact that somewhere in between here, I crossed my x. Let me change color. I crossed my x, therefore I have a root. Unless this is not continuous. For example, if I have a function that goes like this and continues right here. So let's say this is a point here, and this is like an empty point. Then if you choose a point here, and you choose a point here, now this is positive and negative. However, there is no root. And this is why one of the rules for bisection is the function doesn't have to be all continuous, but in between the interval, it must be continuous. So whatever interval you choose, it has to be continuous. So this is one of the rules, is that between the interval you choose, it has to be continuous. The second rule is there have to be 2 opposite signs. For example, again, if you choose a normal quadratic, so if I choose a normal quadratic like this, obviously the quadratic actually goes here, but we're just going to assume this is like x squared, and then it's shifted to the left. Obviously it has a root here, but since not both sides, like this is positive and this is also positive, that looks like an x. Since this is positive and this is positive, bisection will not work here. And now I'm going to go through actually step by step of how bisection works, and you'll know why you need opposite signs. So let's say I choose my point A to be here, and I choose my point B to be, let's say here at the 2 mark. This is B. So what I'll do is I'll calculate the midpoint. I know my A is at 0, and I know my B is at 2, so plus 2 divided by 2 equals 1. So the midpoint between A and the midpoint between B, that would be right here. That's my midpoint. I really wish this shit was gone. Sorry for swearing, but it's bothering me. Okay, so we know now the midpoint is somewhere at 1. So then what I'll do is I'll evaluate the function at 1. I'll be like, okay, f at 1, which is the midpoint, right? So let's say my c equals a plus b divided by 2, which equals 1. We just calculated that. I'm going to evaluate the function at c, and I'll be like, what's the value here? So, so what's the value here? So that's 1. It's somewhere here. Let's say this is like 0.5. So this is 0.5 negative. So let me fix that. 0.5 negative. So then what I'm going to think is I'm going to be like, okay then, which do I shift A or do I shift B so that I get closer to my root, my interval gets smaller? So if we shift A, so if I'm like, okay, no, I bring A here. Well, that means now my new interval is this. And obviously there's no root here. So what I'm going to be like, I keep doing this. So I'm going to be like, instead of this, I will, whoops. Instead of this, I'm going to shift B. So I get closer. So now B is here. I do the same thing now. My new B is at 1. And then so I'm going to do again. My A is same as where it was. So it's 0 plus, what is this? 1 divided by 2. It equals a half. And now I do it again. So the half is going to be, let's see, the half is somewhere here. This is my half. And I'm like, okay, do I shift B or do I shift A? No, obviously, like, okay, now you shift A. And then again, you get the middle point and you keep going. And then as you can see, slowly by slowly, we get closer and closer and closer to our root. And that's how you find the root of a function that is too hard to factor or impossible to factor. So that's about it on how bisection really works. So now we're going to go into the pros and cons. If you don't really get the steps I just went through and you understand more mathematically, I will be going through a mathematical example of exactly like step by step. I'm not going to go like obviously calculate everything, but I'll go through the equations. So now I'm going to go through the pros and cons of bisection. I will be uploading, will I be uploading this? The thing is, I don't know how to upload a PDF on YouTube in the description. I'll have to, I think, upload it to like Google Drive, and I'm low-key too lazy. But if you guys do want it, just comment, and that'll give me enough motivation to do it. So for pros and cons for bisection, is that it's always guaranteed to converge if there is a root within the interval. So if I go back up here, if I choose an interval and there's a root in the middle, or not in the middle, if there's a root within, so if this is A and this is B, or even if I go, if I choose an interval to be A and B is here, like it doesn't have to be in the middle, this is guaranteed to converge for bisection. It also doesn't require complex calculations. So, you just choose points, evaluate at the function, which is usually not expensive. Other methods use derivatives and other complex calculations, but this one, it doesn't cost anything. Even for non-continuous functions, like I mentioned earlier, it will work if the function is continuous within the interval. So if I give you an example right here, if I have a function that goes like this, cuts off, starts here, and then it continues. You could still find, using bisection, as long as you choose your interval to be here, where in between it, this section is continuous. So the whole function doesn't have to be continuous. And lastly, you have control over accuracy, which I'll explain in a bit. But the point is you can decrease the tolerance or increase it. Just keep in mind that the lower the tolerance is, the more iterations it will need. So these are the couple pros. I have them, so I explained them more in depth, but this is just the short format of it. If you want to just read through it, pause the video. Now we're going to go over the cons. So what is the bad about using bisection and why can't we always use it? The first thing is that it's very slow. Specifically, if the root is far away from the interval, it only reduces the search interval by half. Okay, so the way that works is, assume this. Let's assume we do something like, we'll use the same example here, but let's say the way I choose my interval is I put A here, okay, and I put B here. So B is going to be down here, okay? Boom. And then I'll draw this as well. So when you have something like this, what happens is, remember, the first thing is we calculate the midpoint. So the midpoint is here. So that's C. So that's our first split. And then we're like, okay, let's shift B. So then B goes away and B becomes here. Then I calculate the midpoint again. And then I'm like, okay, so this is B. Well, this is C. You're going to evaluate and you're like, okay, I'll shift B here. And then you'll keep doing this. So it splits it by half every time. So whatever your interval is, it splits by half. But obviously this example is very small, but assume your interval is very large. And so how many times will you have to cut in half and shift? And that's why it's very slow. Okay, so that's one of the cons of bisection. Also, the method needs an initial interval of opposite signs. We already went over that earlier. We said when you choose your A and B, your original interval, okay, that's okay here. One has to be positive, one has to be negative. So you see this is negative y, positive y. And that means basically is you have to kind of know your function beforehand, or if you, let's say you have no clue what the function is, so let's say I just give you the same one, but you have no clue how it's drawn. Let's say I give you this. So what typically you'll do is, or what, let's say what I'll do is I'll sub in 1. So I'll do like cos 1 cosat 1 minus 1, and I'll see what this gives me. Now obviously we know cosat 1 will give me some like 0.5 negative. So I know now I have one negative answer, so let's say that's my B. Now I want to find a positive one. Let's say cos at 0 minus 0 equals what? And we know obviously at 0 this will equal 1, and that's positive, so that's A. So you'll have to just sub in random points until you find a positive and negative numbers, and you're like, okay, that's my interval. So you kind of have to know like some things in advance, and if you don't, you'll have to obviously trial and error until you find positive and negative. Also, you have to, the function needs to have a root in the middle, and it has to be continuous. Now obviously, that depends on the function, on how you can check if it's continuous, and how you can check if there's a root in the middle. Obviously, if you know there's a root, then there's no point of using bisection. But mathematically, there are some ways that you can kind of assume. Well, I guess, okay, how should I word this? If it's positive and negative, it's guaranteed to have a root in the middle as long as it's continuous. So basically, all you need to check for is that the function is continuous between this interval. And that depends on the function itself. So it depends on what function you're using bisection on. You have to find a way to make sure it's continuous. Either the whole function is continuous, or it's continuous between the interval. Once you do that, bisection you can use. But, for example, for something like the quadratic, for something like the quadratic formula, it's not positive and negative on both sides, that's the first problem. You know it's continuous, so you can choose like A and B. You know this is continuous, but obviously they're not both positive and negative. So even though there is a root, bisection will not work for this one. Because obviously the half method doesn't work, because the half method depends on the sign. So that's one of the cons as well. I'm trying to think what other cons there are. It also works only for single roots in the interval. So if I have two roots, for example, if I have something like this, or let me make it more. If I have something like this, now if your interval, or actually, let me do this. I'll show you actually both ways. So for here, if you choose your interval here and here, there's only one root within the interval. That's fine. If you choose your B to be here, well, 1, that's 2, so that won't work. It will work sometimes. It's just, to be honest, it's luck. Sometimes you'll run it, it'll work, sometimes it won't. But obviously this is also positive, so it still wouldn't work anyways. But for example, let's say it's something like, ignore that. That's one of the projects I'm working on. There you go. So, for example, here, if you choose, I'm trying to think where you would choose B that would give you issues. Let's say you choose B here. There you go. So let's say you choose B here. This will cause issues. Well, 1, there is multiple roots, 1, 2, and 3. Why does this cause issues? Let's say you split it in half, right? So the first split, let's say it goes somewhere here, and then so you check and you're like positive, negative, that's fine. So you see now B will shift here, whoops, B will shift here, and this will be fine. This will find the root. I just gotta shift my A up a bit. So this will be fine. This will work because you have a root here. You have only one root from your first interval. But let's say your midpoint. So if I take this here, there you go. And then I put B here. When you first split it, right, the first split, the first midpoint is going to be here. You're going to check. So this is going to be your new C, right? You're going to check, are they positive and negative? This is positive. This is also positive. What it's going to tell you? No root. Even though there's a root. And so that's why I tell you, when there's multiple roots, sometimes it'll work, sometimes it won't. Obviously, the first example we did, it worked. This example, it didn't. So that's why we say, like, obviously in math, we don't like randomness. So we say this only works for single roots within the interval. Not single roots for the whole function, but within the interval. And the other thing is it doesn't really give you information about the root. It only gives you a approximation. But I don't think you need to worry about that. I don't think we've done anything in this course that you need to know what type of root it is. So that's that. And that's about it for cons. So this is just the short version of the cons. If you want to read through it or pause and copy yourself. So now that we did the pros and cons, you kind of have an idea of what the requirements are. To use bisection, but I'll list them anyways. So the function obviously must be continuous between the chosen interval. It must change signs at the interval. So A and B must be opposite signs. And the interval must be finite. I didn't mention this, but you can't, for example, have like, you can't have A, comma, infinity. Like that won't work. So both numbers have to be finite, like they're constant, instead of something like infinity. So if you meet these requirements, then you can start to do the bisection mathematically. There are things you can only do once for the whole operation, and some things you repeat. For example, remember when we split it, like we always split it and we did the same math. These are things you repeat. But there are things you only do once. So we'll start with what the things you only do once mathematically. Right now we're going to do bisection mathematically, and then we're going to do pseudo after. But the things you only do once and never touch again. So the first thing would be finding your initial interval. So you see here, first thing you do is you want to choose your interval. Either A is negative, B is positive, or A is positive, B is negative. And obviously, like I said here, you got to find the interval where your root exists. That is the first step. You do it once and you don't do it again. Well, technically, yeah, no, you don't do it again. So this is like the first interval, the original interval, I'm going to call it. That's one of the first steps. The second step is check if it's continuous. So obviously, you want to make sure your function is continuous within the interval, and then you never do that again either. There's one more thing that you do once and you don't do again, but I'll talk about that in a bit. So bisection by hand, of course, after you find your interval, this is the original interval, you want to compute your midpoint. So you'll get C, right? A plus B divided by 2, that'll give you the midpoint that we spoke about earlier. And then after you get it, you want to plug your C into the function, right? So let's say we choose our interval again. This is A, that's B. You have your 2 points. You do your A plus B divided by 2. You get some midpoint in the middle, that's C. You want to take whatever the function is. You want to plug C into it to get some value. If that value is 0, when do you get 0 actually? So let's say my function is, I'll have it between, which numbers? Okay, let's do it between -3 and -2. Let's say my function goes something like this. This is my B. This is my A. and -3 and -2. So to calculate my c, that would equal a plus b divided by 2, right? So that would be -3 plus -2 divided by 2, and that would be 5 divided by 2. Oh, well, -5 divided by 2, which will give you -2.5. So now if we do, okay, so that's my c, right? If I do my function, this new function I just drew, if I do this function at c, which is the function at -2.5, what I'll get is 0. Because I just happen to have the root right in the middle of my interval. And so when that happens, well, you'll say, okay, I found a root. Now, what if it's not 0? What we'll do is, so let's use a different example now. Let's say, we'll use the cos example here. So again, this is my A, that's my B. I have some midpoint C, and let's say this midpoint right here, this equals 0 point negative. So let's say my C equals a negative 0.8. And so what I'm going to do is, okay, if I take the function at A and times it by the function at C, all right? So if I take A, and my A in this case is 0, but this A can be anything. Let's say, but my A is positive in this scenario. So, okay, you know, I'll just rewrite it. Let's say my A in this scenario is not 0. Let's say I chose it here, which is 0. What do I have here? 0.2, let's say. Positive 0.2. So when I do 0.2 times negative 0.8, regardless what that number is, all I care about is the sign. So if I do 0.2, the function at 0.2, which is positive, times the function at 0.8, negative 0.8, well, actually, I made a mistake here. I should correct myself. C is your x. So this would be actually 1.1, right? That's your C, not negative 0.8. When you plug it in, so even here, so my A is fine, is 0.2, and then we'll say my Y here is 0.8, and let's say my Y here is negative 0.8, okay? So now when I plug in for A, what I'll get is this function will return 0.8. And then when I plug in my 1.1 into the function, I will get negative 0.8. So now when I multiply these two numbers, this 0.8 and this negative 0.8, I don't care about the resulting number. All I care about is that the number is either positive or negative. So if I multiply a negative by a positive, I'm going to get some negative number, which is less than 0. So if it is less than 0, that means, as you can see, if it is less than 0, that means C becomes, so I shift B. So first it was AB, right? If it's less than 0, if I do the function at A times the function at C, if it's less than 0, I switch my B with the new C. Remember, if this happens, where it's negative, my B now becomes here. And then I redo the calculations all over again. All right? So that's this step. If, however, it's the other way. So let me, I like to keep stuff clean. So there you go. So the next thing is, okay, if let's say this is not less than 0, let's say this is more than 0. Then what I'll do is, okay, FC now is times B. I'm going to check, is this less than 0? If this is positive and this is negative and I get less than 0, then the root is from C to B, right? So if I split it in half, so remember, so here, let's do a step. Remember, this is my new B now. Let me clean it up. This is my new B here, and this is my new A. I'm going to split it in half again. This is my C. I'm going to now do C times B. And be like, okay, so since this is positive here, this is negative, that means I shift my A here and I get rid of my C, right? Because the root is somewhere in the middle. Oops, somewhere in the middle here. And so that's what happens here, this step. So if this is not less than, so let me return this normally. If this is not less than 0, then I'm going to check for the B point. If the B point is less than 0, that means I shift A. So that's what it depends on, which one you shift mathematically. All right, so let me add that here. Then A becomes C. So that's bisection. I hope I haven't lost you. I'm trying to add as much detail as I can. And I'm trying to repeat myself as much as I can so you don't get lost. Okay? Now there is calculating error, which we'll go over in a bit. This is going to be a little bit long. Sorry about that. But everything I'm saying is stuff like you do need. So I'm not adding any extra stuff. We're going to ignore the error right now. And basically, you'll keep going through this process until you close in on the root and you find it. Right? However, sometimes you don't stop at a root. So let me clean it again. And then sometimes here, like you'll A, B, then you'll shift B, let's say, then you'll shift A, then you'll shift B, then you'll shift A, and then shift B, and then shift A. And then it'll just keep going like this, but you'll never get the exact root. Like you'll never have 0. You'll have 0.0000 something, but you'll never have an exact 0. That's why we need something like errors. And that's what we're going to go over right now. So bisection error. This is the equation for it. E represents your error. B minus A is just the difference between your two intervals. So we have A, and then we have B. And if I take B minus A, that will just give me whatever this is. Okay, so here from 0 to, let's say B is x 1.5. Not times 1.5, like the x 1.5 here. So when I see the difference here, this will be just 1.5. Okay. So that's what B minus A is. And then we divide it by 2 to the n. Why do we divide it by 2 to the n? So I'll go over that in a bit. But just keep in mind, here, this is the original interval. All right, not the current interval you're at. Because remember how your interval changes as you get closer to the root. This is the original interval. N is the number of iterations. Okay. And e to the n is obviously the maximum error. So it's not just any error, it's the maximum error. Now let's go over an example on why this is the maximum error. So if this is my A and this is my B, okay, what is the maximum error I get here? Okay, the maximum error is obviously this. Because if I choose B or A, then like if I say, okay, so B, if I say B is my answer, then the error I have is whatever this distance is, right? Now, obviously, I never know where the root is. So I can't even confidently say what this number is. Because if I knew where the root is, I'd never be doing this. So what is another way I can calculate error? That's why we use maximum error. So now if, let's say this is B, okay? And if I do B minus A divided by 2, right? So I do B minus A divided by 2. Remember we said, actually, let's put this at 2, so it's a perfect number. So B equals 2. So now we'll have 2 minus A is at 0, divided by 2, I will get 1, right? So this is my C. And if you remember from my calculations in the bisection, I always used C as my point. If C is 0, that is my root. I never really used A or B to return as an answer. I always returned C as the answer. So that's why our error is using C. That's why we do b minus a divided by 2. Now the maximum error I can get here is this distance. That's why it is 1. Why is this distance the maximum error I can get? Because let's say a is at the root. The root is literally at a. But obviously when you're doing this, you don't know where the root is. You just happen to choose the root exactly at a. And then obviously you do b minus a, you get your c, it's in the middle. If this is my answer, can I get a bigger error than this? From where my a point to my c point? No, you simply can't get a bigger error. You can get, like, if the root was, okay, you know what? If we were here, back where we were, and remember, my c was here, the minimum error, the maximum error is still this. I mean, yeah, I know the root is here, but I am guaranteed, at least I can guarantee that this is the maximum error I can get. And I can calculate this, right? This is just b, the difference between c and a. So if I do b minus a, if I take whatever distance this is, divided by 2, aka my c, that would be this distance, right? So keep that in mind. This is why we use the maximum error. What was I going to say? Oh, I wanted to mention on why we use the n. Why is the maximum, where was I? Whoops, this is where I was. Why is there an n here? Because, so if I divide it once, so if I do this as a, I do this as b, and then I divide it once, my c will be, actually instead of making a line, this is my c at 1, right? Now my error is b minus a divided by 2. B and a being the original, okay? Now, if I redo this one more time, so my b shifts, right? And then I divide this again, and I get something here. So this is my new c. Okay, now what's my error here? This is simply 2 to the 2. I have to think about that for a bit. Because you split it twice. So now it's b, the original b, minus a, divided by 4. So remember, if b was at 2, now what I have is 2 minus 0 divided by 4 is 2 over 4. And it's what I got here, which is my 0.5. Okay, or 1/2. And so that's why we square it. Now, one way you could do this to get rid of that n, you could say, okay, what if I calculate my error? Instead of using the original AB, I will use my current iterations AB. So I will, instead of using the original A and B, I'll use my new, so let me remove these. I'll use my new AB. Then in this case, you don't need to square it. You'll just do your new AB divided by 2. And that's your new error. And so, but if you want to keep using the original one, instead of the new, you just keep the square. And then the square is whatever the number of iterations you're at. So if you're in the first iteration, you just divide it by 2. If you're in the second iteration, you divide it by 4. If you're in the third iteration, you divide it by 8. And you keep going that way. Okay? And so that's about it. Now, for tolerance, what is tolerance? If you go to the lecture before this one, the first one, I talked about error and tolerance and what they represent. The tolerance is the maximum error you want to handle. Okay? So let's say this is my C, and I'm like, okay, actually let me choose again new numbers. Well, not new numbers, but we'll keep B at here. Let's say my tolerance, I say, tolerance, actually I'll make it in red so it stands out. Let's say my tolerance is like 1. That's my tolerance. So if my error is 1 or less than 1, then accept it. Like, that's okay. Like we don't have to get closer, because remember how I said sometimes you just keep going and then you don't stop. You never get the exact 0. This is why we give tolerance, and that is the whole reason I start, like I was explaining error, in case you forgot. So now let's say I do the first iteration. Obviously my C is here. And then I'm like, okay, what's my error at this point? So I'm like, so then that's b minus a divided by 2, which equals 1. Now that's exactly a tolerance. Let's say you don't want the exact tolerance, you want less than. We take another iteration. So this becomes my b, and then I calculate my c, which is 0.5. This is my c. I'm like, okay, what's my new error? And let's say I'm using the current iterations interval. So this would be 1 minus 0 divided by 2, which equals 1/2. That's my error. Is my error less than my tolerance? Yes. So what I could say is, okay, my answer is C equals 0.5. The root is at C plus minus the tolerance of 1. Okay? Or, actually, I can't remember if he uses plus minus the error. I'm pretty sure it's plus minus the error, actually, not the tolerance. Plus minus the error, okay, which is obviously 0.5. And so that would be your answer, assuming it falls within your tolerance. Obviously, your error is the half. And it just, by the way, it just happens to be our C and our error is the same number. This is not always the case. It's just, I'm using a very simple example, so it is. But usually it's different. Like your C will be at X, because C is X. So if the root was like set somewhere here, and here, let's say your root was somewhere here, then your C will actually be like some negative 3.2. And your error is obviously just the error. So keep that in mind. This is just a simple example. That's why they're the same, but it's not necessary. Okay? So that's basically error and tolerance. Now, for tolerance, how do you know what tolerance to choose? It all really depends on the number of iterations you want, or I guess the tolerance you want to accept. Let's say you're cutting a sheet of metal and you want it to a precision of plus minus 1 centimeter. So your tolerance is going to be 1 centimeter. So that's how you choose your tolerance. I'm trying to think if it depends on the function. It doesn't really depend on the function. It just depends on your application. It depends on let's say what the prof wants or how accurate you want it. Yeah, it doesn't really depend on anything else. But you do need the number of iterations for you to accept such tolerance. Why is that? So in order for you, so let's go first on how you get your number of iterations n. If you take your error, the original equation we went through, and then we solve for n, you just rearrange, right? So if I'm not going to complete the whole rearrangement, but just so you kind of get an idea of where this came from, you multiply by 2 to the n and you bring, so it will be 2 to the n equals b minus a divided by e to the n, right? And then what we'll do here, we want to bring n down, we'll ln, I think it will be like n ln 2 equals, and obviously if you ln this side, you ln the other side, and then from here you know like how to isolate. This is just basic rearranging stuff. After you've done your rearranging things, this is your final equation you'll come up with, where your E, I know this equation, your E is the error. Your tolerance technically is an error, okay? It's just the amount of error you're willing to accept. So we change it to epsilon, saying that it is the error, but what type of error does this represent? This represents the error I'm willing to accept, and that's why we name it epsilon, okay? So that's why we have a different looking E there. Once you plug in your original interval and you plug in your number of tolerance you're willing to accept, that will tell you how many, the minimum, so here I'll write it to the side actually, n is the minimum. That would be the minimum. Would it be the minimum? I feel like that would be the maximum. Actually, yeah, this is the max. Whoops. This would be the maximum number of iterations to reach your tolerance. So what the function is basically saying, or what this mathematical problem is basically saying, it's saying the amount of tolerance you put, this is how many times you'll have to divide your function so that you get this amount close to the root, right? So if n was 10 and my tolerance is some number, what it's saying is you'll have to keep doing this split 10 times until you reach that tolerance. Now, why is it the maximum and not the minimum? Why is n the maximum number of iterations, but it's not the minimum? The reason for that is because we went over this example earlier. If you paid attention, or if you just figured it out, then you're a genius. If this is my function, that's b, that's a, right? And this is my root. If I calculate my b minus a divided by 2 for my c will be exactly at the root. So as you could see, I just happen to be one iteration. N equals one iteration and I got my root. So the minimum number of iterations is when the root is exactly in the middle. But n gives you the maximum, which is when the root is exactly at one of the intervals. So if b was here, right, it will tell you how many iterations you will be doing in order for you. So let's say, so this is the root. Obviously, let me do that in red. This is the root. That equation I showed earlier for tolerance will show you how many iterations you got to do in order for you to get as close to your tolerance as you want. So this is like the maximum number of iterations you need to do. This is like a worst case scenario. Okay? So usually what you'll do is first you'll choose some error and you'll get your n. And then you'll use your n in order to calculate your error. Well, not in order to calculate your error, but in order to stop the function. Because remember this, there was no stop here. The only stop was when c is 0. And this is why we don't ignore this anymore now that you learned error. Now, every time you split your function, you're going to calculate the error. You're going to see if the error is less than the tolerance. If it is, stop. The other condition you can check for is if you reach the n maximum. Okay? Because let's say you keep going, your error is getting smaller, but you're never really reaching the tolerance. And your function just keeps going. Just keeps going, and it's taking forever, and you're like in a while true loop. It's not ending. This is n, because this is our maximum. N is your safeguard. Once you reach n number of iterations, if your error is not less than your tolerance, you just exit. That means the function just simply doesn't converge. There's just no root. There's something wrong. Okay? But obviously, if you've made sure it's continuous and it's positive, negative, there should be a root. This is just an early exit condition. And that's how you can calculate your n. And that's how you can calculate your error as well. So now we went through the mathematical problem. Now just a simple pseudocode. We'll go through this very quickly. I don't know why there's a C there. Can I remove this C? Hello? Okay, I guess not. Don't worry about it. So for the function, first, obviously, you want to multiply the interval. And you're like, so actually, let's start with the parameters. You get the function that you're trying to find the root for, the interval you chose, and this is your tolerance, epsilon. Okay? The first thing you check is, are these both negative, positive? So if this is positive, negative, or negative, positive, your answer will be less than 0, not more than. So if it is more than 0, that means they're the same sign. Because if this is negative, negative, that gives you a positive, aka more than 0. And if this is positive, positive, again, that's more than 0. So then you exit right away. You're like, well, bisection doesn't work unless they're different signs. Therefore, we exit. Okay? Now, assuming you pass this condition, you don't exit. One is negative, one is positive. You start your iteration at 0. You calculate your first initial error using your original original interval. Then we start a while true loop. This loop just says once the error, keep going as long as the error is more than my tolerance. When the error is less than your tolerance, that's it. You accept this solution, right? Because you have this level of tolerance and the error is less than that. You're happy. So you exit. So as long as the error is more than epsilon, keep going. That's what this says. All right. Now, obviously, we start with the iteration. We add the iteration plus 1. We calculate our C, and then we evaluate our C. If C is 0, we return C. That's the root. If A times C is less than 0, then B becomes C. Else, A becomes B. Right? And then at the end of our while true loop, we calculate our new error. Your error variable gets updated. And then we go back to the while true loop. Is the new error now more than epsilon? It is. Loop again. Split the function, blah, 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 until eventually your error becomes less than epsilon. This becomes false. Your while loop stops. And then you return C because obviously your error is less than your epsilon. Now remember, we calculated n. We could put a safeguard. And we could say, and while n, so while the error is more than epsilon, and while n, we can choose a different variable. Okay, actually here, we'll define here, like max n. So remember when you calculate your n and you choose your tolerance, we could do our max n is 10. And then what we'll do here is, okay, while n is less than max n. Okay, so remember, the initial one is 0. Is 0 less than 10? Yes, keep going. And then you're going to keep going. You're going to keep adding until this number becomes less than or more than. So let's say this becomes 10. Is 10 more than 10? No, but remember, we didn't put equal sign. We just put less than. So therefore, this will exit. And look, we've reached the maximum number of iterations. Again, this is a safeguard, so you don't have like an infinite while true loop. And that's about it. This is everything you need to know about bisection, how you use it, what the code for it is, error, tolerance. I went very in depth, so you really explained it well because you will be using this for assignment 2. So unless like you kind of understood everything, you wouldn't be able to. Hint for assignment 2, the function. This is like the cherry on top. If you stayed this long, you're welcome. And if you did miss the lecture, or if you don't understand what he was explaining about assignment 2. Now, possibly if you're a later year, the assignment might be different. But for 2025, semester 2, or winter semester, the function he's going to give us is, I believe it goes something like this. Okay? And he tells you to find the root. So obviously this has no root, but what he tells you is find the root at some constant c. So he tells you, like, let's say this is 2. Actually, let's not use c. Let's use like I don't know what to use. Z equals 2. So he'll tell you, okay, find where this function crosses z at 2. And so obviously that would be here. So technically this is a root. So imagine your x-axis shifted upwards, and your x-axis now begins at y equals 2. Okay? Therefore, now that you know how to use bisection, all you got to do is shift your x-axis up, and then calculate for your new root here. Okay? So that's the hint for assignment 2. And that's about it. I really hope you understood everything. I know it took long. But I really wanted to be very thorough with it because this is one of the very basic methods and it's the backbone of computational, which is for root finding. So I hope you guys learned something. Next video will probably be Newton's method. And I'll see you guys on the next one.